Okay, I've already done part 1 of sac436 problem number 1, and now it's time to do part 2. Part 1 involved finding the magnetic field at point P, some unspecified but fixed x, y coordinates associated with it, due to the wire along the negative half of the x prime axis. And in fact, in part 1, we found that that contribution to the magnetic field at point P was in the z direction and had magnitude mu0 I over 4 pi y times 1 minus x over x squared plus y squared all to the 1/2 times k hat, that is in the plus z direction. Alright, now we want to find the magnetic field at point P due to this vertical wire segment. We're going to use the Biot-Savart law. We'll take an infinite set of tiny infinitesimal pieces of the wire. Each one I'll call dl. Each one makes a contribution to the magnetic field at point P1, which I'll call dB2. Each one makes a contribution in the plus z direction, which you can get by the right-hand rule. Point the thumb of your right hand in that negative y direction. The fingers will curl around the wire, indicating that the magnetic field lines make loops around the y-axis, and the fingers, as they curl around, will be pointing outward as they punch through the plane of the screen, so in the positive z direction. So we're getting every component is a z component, and dB2 in particular will be in the positive z direction. I'll call this position vector for the point at which we wish to find the magnetic field with respect to the little wire segment that we're dealing with, vector R2. And let's talk about the magnitude of it for a second. First off, we can look at it as consisting of a y component and an x component. And the x component in magnitude is going to be exactly x long, where x represents the position variable, or the ordinate, that's the abscissa for point P. So I'll call that x squared. I'm going to use Pythagorean's theorem to get what R2 is. And then this distance, right here we got a distance y. We'll characterize the position of the segment, the little wire segment that we're dealing with, as by means of coordinates in the primed coordinate system. So I'll call that position 0. The x value is equal to 0, or the x prime is equal to 0, and then just y prime. And it should be noted that y prime is a negative value because we're always down below the x-axis. So this distance to the wire segment is actually minus y prime. So for instance, if y prime is minus 3 centimeters, then this distance is minus 3 centimeters, or just 3 centimeters. So the total distance from total vertical distance, total distance along the y-axis, the component of this R2 vector that is along the y-axis in magnitude is going to be y plus the negative y prime, or y minus y prime. And so the R2 in magnitude is going to be the square root of x squared plus this squared, which is y minus y prime. all squared. Alright, dB2 mu 0 I is the amount of current in this leg, divided by 4 pi times dl. I think I put a vector sign over there, and we're just writing down the generic expression here. dl crossed into R2, not quite the generic expression because it does involve our specific position vector, but divided by R2 squared. So that is the contribution to the magnetic field at point P due to this infinitesimal wire segment carrying a current I is going to be equal to mu 0 times I, the amount of current that it has over 4 pi, times dl, the length of the little wire segment, crossed into R2, where R2 is the position vector of point P, the empty point in space where you want to find the total magnetic field with respect to the wire segment in question. And this is actually supposed to be over R2 cubed, with a magnitude, that distance cubed. This is actually an inverse square law in that I get the distance R2 up here and the magnitude of the vector, and to the 1 power down here to the 3 power. One of them cancels out, so it's actually a 1 over R squared law. Every contribution is going to be in the z direction, so dB2 as a non-vector, I'm just getting the component in the z direction at this time, will be mu 0 I over 4 pi. Now dl is going to be a step. I'm going to be integrating from 0 down to minus infinity, so I'm stepping in negative directions. So dl itself is a minus dy. Actually, I think I'll just put that in there as dy prime at this stage. dl is dy prime, but keep in mind that this is a negative value. A step, like if I go from minus 3 centimeters to minus 4 centimeters, the delta y would be minus 1 centimeter. So every dy prime is a negative value. And I'm going to worry about the algebraic sign, make sure that it comes out so that we get a positive magnitude for the component of dB2 in the plus z direction. And then conceptually I understand that this dl crossed into R is one vector, in magnitude anyway, times the component of the other vector that is perpendicular to the first vector. Well, in our case, the component of this R vector that is perpendicular to dl is the x. So I'll just call that x, and then over the R2 cubed, and then with x being a positive value, we are over to the right, and dy prime I understand is a step in the negative y direction, so it's negative. This would come out negative, so I want it to be the component of b in the plus z direction. So I'll take the negative of it, and I get a positive contribution to b in the z direction. There's a little bit of conceptual thinking going on there. So let's take a look at this where we let the math actually do the work for us in terms of direction. So I'm saying this is the component or the contribution to the magnetic field at point P due to this tiny little wire segment carrying a current I in the negative y prime direction. If we look at it in terms of IJK notation, I can say that this equation becomes dB2 is mu 0 I over 4 pi times dl, which is a step in the minus z direction. I'll call that dy prime, and remember I am going to be integrating from 0 to minus infinity, so that is a negative quantity already. So times j crossed into, that represents this little vector dl in the minus y direction, minus y prime direction you can call it. And then I'm supposed to be crossing that into R2, which I can express as a step over to the right of magnitude x. So I'll say x times I, and plus a step upward of magnitude y minus y prime. So I have a y minus y prime times j, and that would be equal to mu0 I times 4 pi times the j crossed into I gives me a minus k. Point your fingers in the direction of the plus y axis for the unit vector j when you're crossing j into I. For the right-hand rule for the cross product of two vectors, you're supposed to point your fingers in the direction of the first vector, and then arrange the hand so that if you close the fingers, it'll be pointing in the direction of the second vector. So I got my hand held out with the fingers pointing toward the sky. Now I face my palm to the right along the positive, my right along that positive. So the palm is facing in the positive x direction. That way if I do close the fingers, they tend to point in the positive x direction. And I find that my thumb is pointing into the screen, which is in the minus z direction. So j crossed into I is minus k. And I'll have the dy prime and the x there. So I get a minus dy prime x. And then all this stuff, I think I put in the cross product, but I never put in the R2 cubed. There it is, and I still have an R2 cubed over here. And I did say that j crossed into I was the minus k. So here we see I've got it in vector notation instead of just having the magnitude of the z component, but I get the same result as what I had up here. This was the z component, and it is in the positive k direction, and same thing here. We see that the piece that I've got out front, which would represent the magnitude of the z component of the vector, is exactly what I've got up there in that expression. So I'm actually going to erase this part. And move on here. So I've got to integrate that. I'll go ahead and put integration signs on both sides. This side just the sum of the infinitesimal, the infinite set of infinitesimal pieces gives me the total. So that's just B2. I don't have to use math tools to get that. But over here, I'll be integrating, I said, from 0 where the current starts down to minus infinity. Working in the same direction that the current goes, so 0 to minus infinity. This x, the fixed position of the point P, the fixed value of the abscissa for specifying what point I'm calculating the total magnetic field at, that's a constant. when I sum up all the contributions due to all the little DLs, I pick different pieces on the wire, that point P stays fixed. It's the Y prime that's varying. X stays the same. So I can factor that out. Right, B2 so sum of all the pieces gives me the total contribution from that vertical segment of the wire, and it's equal to minus mu 0, I'll take that X over there, the constant, times I, all divided by 4 pi, and then times the integral of dy prime over, and by the way that's from 0 to minus infinity, and I need R2 cubed. R2 cubed. R2 itself is this expression, which I can write as x squared plus y minus y prime, all squared, to the 1/2. And if I cube that, I can multiply the exponent by 3, so it'll be that same expression raised to the 3/2. And there we go. If I compare it with the integral in the table of integrals, let's see what that one looks like. Got from the table of integrals, I got one that reads dx, integral of dx over x squared plus or minus a squared all to the 3/2 is equal to, and then call it the antiderivative of that 1 over x squared plus a squared all to the 3/2 is a plus minus x divided by the constant squared times the square root of the integration variable squared plus or minus the constant squared. So we've got something very similar to that. The integration variable, I've got it on the right hand side. I think I just want to copy that over. Mu 0 x I. I'm going to copy it over with this variable piece on the left so it looks a little bit more like what we have. That'll be the integral from 0 to minus infinity of dy prime divided by, I'll write it, just writing that stuff inside in the denominator in the opposite order. Squared plus x squared all to the 3/2. And now it looks very similar. I'm using the plus sign in the denominator here. So all this plus minus stuff, in our specific case, we're dealing with the plus part, so that'll make things a little bit simpler looking anyway. And then I got a piece involving the variable squared plus a constant squared. X is constant over the integration. All of the 3/2. It looks like I got pretty much the same integral, except instead of just the variable of integration squared, I got something minus the variable of integration squared by comparison. So I'm going to make a variable substitution to make it look even more like this integral so that I can write down what the answer is. I'll call this thing that's being squared, I'll call that v, and I'll try to make v the variable of integration so that it'll just look just like that one. So I'll call v, let's make v be equal to y minus y prime. Then dv, let's see, the y is a constant, so the differential associated with it is just 0, and again, it's going to be minus dy prime. And for the limits of integration, v when y prime is equal to 0 is going to be just y. And v when y prime is minus infinity, if that's minus infinity, I get y plus infinity, which is just infinity. So the upper limit here is infinity, and the expression for b2 in terms of the integration variable v becomes, let's see, I'm going to put dy prime is minus dv, so I'll put a minus dv in here for the dy prime, and the minus and a minus there cancel out, so I won't have any minus sign in the expression for b2. So mu 0 times x times I, all divided by 4 pi, and then times the integral from y up to infinity of dv. Okay, and I already took care of the minus sign. It was used to cancel that one out. All divided by v squared. This is where the substitution was designed to make this look simpler, and it does. All to the 3 halves. Okay, now it looks just like the integral from the table of integrals. Although I got different variable names, and even confusing here. My variable of integration is the v, so the v is playing the role of x, and the constant here is actually called an x. The x here is playing the role of a. So let's look at the answer here and see if I can get that in there, despite that redundancy of the symbol x having one meaning in the generic expression and one meaning here in this integral that we're actually doing. So I'm supposed to put the variable of integration there, that's a v. Supposed to put the constant here squared, that's the x squared. And then times the square root of the x squared plus the variable of integration squared. No, plus the constant squared. And by the way, this x squared is supposed to be the variable of integration, so that's actually a v squared. Couldn't quite do it without a mistake, but I think I'll get it right in the end here. So there's our variable of integration squared, the v squared, and then plus the constant squared is going to be plus our x squared. And just want to make sure that was supposed to be the constant squared, and it is. Okay, and I got to evaluate that from y, from v is equal to y, up to v is equal to infinity. I'm going to put brackets around this point, evaluate that from y to infinity, and just be multiplying it by this constant up front. The x is a constant, so that becomes a part of the constant. I'm going to cancel out, actually, one of those x's. So I'll wind up with b2 is mu 0I over 4 pi x times this expression evaluated in the limit as v goes to infinity. I think I'll just plug in an infinity for v, see if we can make sense of that. Then we'll have divided by the square root of infinity squared plus x squared, and then minus the same expression evaluated at the lower limit, and to get y over square root of y squared plus x squared. Alright. We understand that this expression represents the limit as v goes to infinity in these two places, but we wind up with something that amounts to infinity. Well, infinity squared plus x squared is infinity squared. Infinity divided by the square root of infinity squared, which is infinity. So we got a 1 in that first term, infinity over infinity, and then 1 minus the y over, and I think I'll reverse the order inside there. Copied it down in the other order when I wrote the answer in part 1 for B2. But now we've got our expression for B2. That's actually the answer for this part. If I put, I'm going to clean up that subscript a little bit. Doesn't look much like a 2. If I express this as a vector, all I have to do, since we established that all the pieces were making a contribution in the plus z direction, just multiply that by k to indicate that it's a vector in the plus z direction. From part 1, we had B1 is equal to mu 0 I over 4 pi y times 1 minus, I'm going from memory, let me take a look. Yeah, it was x over square root of x squared plus y squared, all times k. So B is the sum of those two. And therefore B is, go factor out the mu 0 I over 4 pi, mu 0 I over 4 pi, and then for B1 I gotta multiply through by 1 over y, so that'll be a 1 over y minus 1 over y times all this stuff. And for B2, I got to multiply through by 1 over x. So I have 1 over x minus 1 over x times all this stuff. Or I'll put in the part from B2 first, the 1 over x part, and the part from B1, the 1 over y part. And then minus, I go y over, I'm getting this B2 part, x times the square root of x squared plus y squared, and then minus this piece here, the 1 over y, times x over the square root of x squared plus y squared. And there's B. I think I'll put those last two pieces over a common denominator. So let's multiply upstairs and downstairs by y in this case, and upstairs and downstairs by x in this case. And then I've got same denominator for these last two terms, so I can express B as mu 0 I over 4 pi times 1 over x plus 1 over y minus, both terms have a minus, so I'll put the minus all the way out front and call that x squared plus y squared up top divided by xy times the square root of x squared plus y squared. Of course, this top part I can express as the square root of it squared, which makes it so that I got square root of x squared plus y squared on the bottom, and then the same thing upstairs squared, so I'll cancel out one of those. And express the final answer, somewhat simplified, as mu 0 I over 4 pi times 1 over x plus 1 over y minus the square root of x squared plus y squared all over xy. And that's the final overall answer for SAC 436, problem number 1. Oops, not quite. Better put a K in there. So I've been leaving out that K quite a bit here. Ran out of room up there. Any place else? There we go. Alright, let's call that the final answer for SAC 436, problem number 1.